So I think in the introduction you mentioned the effect of energy. I think energy transfer on the structure changes. I think first you mentioned your motivation is to investigate the effect of energy transfer between antenna chromophore and the catalytic factor on the structure changes. But actually, I think this structure changes is not induced by energy transfer, right?
Yeah. Did I mention it?
Huh?
Did I mention like that?
Yeah, to
You
me.
give the impression.
Yeah, because I think go back to the yeah. This means, at least to me, this kind of impression. I get this kind of impression. So I think in this case, the HDF does not play a role as antenna cofactor. How to say? Yeah. We don't investigate the function of antenna cofactor, right? Antenna function in this story. So
I mean, like, because before we perform TRSFX experiment with HDF, we didn't know if there's any structural change on HDF. So after collecting the data, we realized that there's only two residue around HDF move a little bit, but HDF there's no significant difference density around HDF.
Yeah, I mean, I think energy transfer occurs within much faster time region.
Yeah.
So that's why before correcting data, we know that we cannot observe the structure changes upon energy transfer. So that's why the introduction may be.
Yeah, I mean,
I think you need to introduce another slide there. You see? So I completely agree with you. So the point is that at this point you say, oh, it's a good system to study the antenna system, isn't it? Okay. So as a kind of, however, studying this kind of stuff in the energy transfer itself takes place in, say, femtoseconds to picoseconds, which is a very complex time region to study because signals are weak, reactions are super fast, very little is understood. So as an initial approach, we wanted to look into the protein dynamics as an effect of, or as a function of having the antenna or not. And so my study is on the structural effects on the protein dynamics due to the presence or absence of the antenna. You see what I mean? So that means that basically you just need to add an extra slide behind it. You see, to provide a kind of justification of your goal. You see? So I completely agree with you. But again, I don't think it's unrescuable. Let me say it like that. I think that it just needs one slide to center your topic, which is, okay, so this looks like, so for example, what you could do is, can you go, I was going to suggest a couple of changes here, but if you go further down to Yuhei's paper, So you have his paper. Yeah, this one. So I would make this much simpler. Okay? And I would combine it with the photolysed activity story that you have before. And then you say, so that one,
This one.
the lower one.
Uh-huh.
There. Those two you have together. And as C, we now know that photolysed activity depends on 8-HDF. And there are two options here. That it depends on 8-HDF because it increases the quantum yield of the reaction, okay? Or because it does something by modifying the structure. And we have seen from another paper that actually the presence of 8-HDF stabilizes the fully reduced catalytically competent structure. Therefore, we have reason to believe that there must be some structural changes beyond simply increasing the quantum yield. There must be some structural changes there that stabilize the FAD in the presence of 8-HDF, which are not there in its absence. Isn't it? Therefore, this is what we want to study. So before we go into a super long time, into a super short time frames and so on, we want to study how does the protein photocycle, how are the protein states affected by the presence of 8-HDF. You see what I mean? And so then you have a really good story, isn't it? So yeah, in the future we will go into the femtosecond time scale to look at how the energy transfer works and so on. But right now, we have reason to believe that the presence of 8-HDF is going to give us big conformational changes on the protein. Let's see. You see?
Yeah. Sorry, I just cosplayed as reviewer.
Yeah, absolutely. That's the point. That's exactly the point.
Yeah.
And I think it's great. Yeah, so, but you see that it's an issue of the structure of the introduction. You have all the elements there. You just need to write them, to put them in the right order to avert that question. You see? So, any other issues?
For slides, I think there some modification should be done. Regarding regarding the TRSFX study without 8-HDF, I think you just show the structure, not detailed mechanism or something like that. I think in the slide, what we want to say is we have observed the structural changes in 3 loci, mainly 3 loci. The Freddy side, TPP, and the C-terminal region. These loci are slightly far away, right? So I think you just put the overall structure. And what I did in some presentation is put the global structure and put the difference density map. So if you superimpose the DF4 map into the overall structure, then you can see 3 concentrated spots. Yeah. So then we can see 3 spots. So yeah.
I think that makes a lot of sense.
And also the real story. So Q390 and I think after structure changes, after occupancy changes in Q390, E384 movement will be observed. Then N395 will move. And this story is really nice. And maybe I think there should be a lot of discussion.
Should be ready.
Yeah, I think most of chemists want to know the driving force.
Yeah. Exactly.
So I think it's difficult to, but I think you really need to take care of.
Yeah, I agree with you. I agree with you. Any other comments, questions? I mean, I think the first thing that you need to do, in general, I find you're a bit too technical. And I think in a presentation, especially because this is what you hope to present in your defense, isn't it? So you have to be less technical at that kind of situation. So that means, first of all, I would make the introduction a bit shorter, trying to make it a bit shorter. Again, as I mentioned, you can combine this part of the slide with you guys' paper to provide sort of an overview of the motivation. You see what I mean? So then, if you go in the beginning, so I think that you should, first of all, I don't like all those text rules. I think you should just keep the figures and remove those text rules. You can have that as notes for yourself, just don't have them. Nobody cares about them and you're discussing them. Yeah? Second thing, you should, here the thing I missed was that you're missing an explanation of why antennas are important. Indeed, why is an antenna chromophore called an antenna chromophore? Well, because it acts like an antenna, like a television antenna, or like a radio antenna. If you want to, this was some years ago, but if you remember, there was an iPhone that had an antenna defect, where if you held the iPhone in the wrong way, you were covering the antenna, and all of a sudden you would lose connectivity. So what I'm saying is, you can start with something like that, explaining what is an antenna good for, and why are antennas required. So in the case of photosystem 2, there are two reasons why antennas are required. The first one is because the what's called the active center is actually not particularly good at absorbing light, isn't it? And the second one is filtering multiphoton effects. So by jumping like a million times around, you ensure that only the right amount of energy will be trickled down to the oxygen evolving complex, isn't it? And so that means that as a result, you're going to get the right amount of energy. You're not going to get multiphoton effects or anything like that, because remember that the effect here of multiphoton effects is also have free superoxides flying around, which is not good. Like basically, so that would be point number one. Yeah? Then when you go to the next one, okay, then you can explain why is this much easier, isn't it? Because there's a single one. And here, because you've already explained that it increases the quantum yield, you can immediately say here, well, in the absence of the antenna, these enzymes are still active, but with a very low extinction coefficient, and thus the effectiveness of the reaction in vivo is much decreased. Something like that. So, okay, see what I mean? Then it holds a bit better, isn't it? So then, you explain your target, isn't it? You're interested in checking what happens in the presence of an antenna. And I would go more general, just like you mentioned, just more general. Okay? These enzymes can exist in the presence or in the absence of the antenna. We're interested in checking what do antennas do, both structurally and functionally. Okay? So then we go for the next step, and then you explain here what's the procedure and so on. Now, in this case, okay, what I would do is concentrate on the photochemistry, and that's it. Okay? And then maybe in the photochemistry, so once you make it a bit bigger, in the photochemistry, you can possibly do two slides. Okay? One where you show this one, and then where you erase the little blue lightning, and have the 8-HDF receiving the blue lightning, and then sending sort of a squiggly line or something like that directly the energy into the FAD. You see what I mean? And then you say, see, up until now, this is what we have been looking. Now we want to look at what happens when this happens. And then you have the 8-HDF and the squiggly line, the receiving the light and the squiggly line going on the FAD. Do you see what I mean? So that gives you a better overview of what's happening. Okay? Then, in this case, I would delete the C-terminal unfold. You're not looking into it at all. Why confuse people about the C-terminal unfold? Isn't it? That's not part of your, that's not going to be part of your talk.
I'm thinking because for C-terminal, because the important time, the important time delay of C terminal is like 2 milliseconds. So
What?
in my case, I don't know how to analyze it.
That's why you don't have it in your talk, remove it. Okay? No, then you spend a bit of time, you spend time here explaining that, and you're going to concentrate on the protonation. Isn't it? So concentrate on the protonation. You can mention it. You can say, ultimately, after several milliseconds, this whole photochemistry derives into unfolding of the C-terminal helix in the system. So, and we believe that this is the signaling state. That's it. Do you know what I mean? Don't go into any more detail. I think that the detail here, you need to make sure that your audience understands the standard protonation pathway. This is the important thing, because that's where most of your things happen, isn't it? So don't get distracted by that. Concentrate on the, so you give it a general overview, and you say, see, within the first couple of nanoseconds, mostly it's the FAD dot minus that gets stabilized. Then in nanoseconds and microseconds to milliseconds, we get the protonation of the FAD, which further stabilizes the FAD. And then in our previous studies, in very long time scales, in the milliseconds to hundreds of milliseconds, we get final unfolding of the C-terminal helix, which is the signaling state. You see what I mean? And there you are. But you spend most of your time on the protonation pathway, because that's where you're going to spend most of your talk, isn't it?
Yep.
So you give this kind of general mechanism, and then you go, okay, as we will see later, I would like to concentrate, or something like that, from these stages, today I would like to concentrate on the transient protonation pathway. Let's go a bit more into detail into how that works, and then you show that. You see what I mean? And then you're ready to go later. But you make clear that you're going to concentrate on this one. Okay? Help your audience to understand where you're going with it. So then please continue. As I mentioned here, you can do it much more simple than this. Okay? You don't need any of the spectra or anything like that. The only thing you really need here is that the kinetic is about 4.5 times fold slower in the presence of 8-HDF than in its absence. That's all you need from this paper. So what do you do? Here, the only slides you show, or the only figures you show, are the ones for activity. You say, see, in the presence of 8-HDF, we have much better reaction, isn't it? So how about so we have photolysis activity basically only happens in presence of 8-HDF. But as I mentioned before, this could be because in the presence of 8-HDF, the extinction coefficient is so much higher, isn't it? However, recently, some papers, papers by Hosokawa et al., or in a paper by Hosokawa et al., it has been shown that the reduced redox states of FAD are much more stable in the dark in the presence of 8-HDF than in its absence, at about a 5-fold increase in stability. Okay? What could the reason for this be? Well, the only explanation, or the explanation of the higher extinction coefficient doesn't work anymore here, because we're not talking about light absorption anymore, isn't it? There must be a protein dynamic induced change by the presence of 8-HDF. This is what we want to study. You see what I mean? So in that way, you follow your introduction and you bring a final story that you want to tackle, which is what is the structural effect of 8-HDF. You see? So then you go for the next one. Okay, so this guy here, okay, I mean, that's not bad. The only issue is, I think we work at 450 nanometers.
Really?
Yeah. I think that for all of these, we work at 450 nanometers.
I'll check again.
Check again, okay? This 408 is for MMCBD2. So the high extinction coefficient of 8-HDF comes at about 450. So we normally work at 450. Okay. So okay, then yeah, this one looks very nice. Okay. What I suggest here is, first of all, you don't see that much of a difference here. Highlight that.
Oh, okay.
Okay, so see, we don't see huge differences, and that's because all changes are rather local. Okay? Secondly, write somewhere how many crystals you use. Okay? Under each of them, derived from 50,000 crystals, 250,000 crystals, something like that. Do you know what I mean? Write it down. People will appreciate how much work that has gone into it if you actually write it down. Okay? Secondly, highlight the resolutions. You're well within the range where you can see differences in bond length. That's not something that with the nature chemistry we could do. So then in nature chemistry we were at about 2 angstrom. Here you're within 1.5 angstrom, and remember, bond distance is about 1.44. So that means that you are within the resolution where the difference in bond length should be detected. Okay? I mean, very high resolution, very high quality of all of your data. Okay? So make sure that you mention this here. Okay? That your data has very good quality. Okay? Then, this one, I would suggest that you write more residue numbers.
Okay.
Because if I wouldn't know what I'm looking at, it would be very difficult for me to know what you're talking. And the only one that you mentioned here is Q390. Okay, so please provide a couple of extra ones. Okay. Beyond that, I think that's fine. I don't know about this one. What happened here? It's a bit difficult to see what you're pointing at. It just looks like it just disappeared. Okay. But I think maybe what you want to do is when you do this, just keep the square, which is actually where you have there. Keep the square still in full color.
Yeah.
Do you know what I mean? So that basically we know where we are in the full structure, and we know that we want to concentrate on this structure. Okay, so this one here, I suggest that you add a dark state with the FO, 2FO minus FC density. So that you show that clearly in the dark state, you can see blobbies for both of them. Do you know what I mean? And maybe, for example, for the last one, for the 3 millisecond or something like that, show also the density. So we can see that we have blob only for the, the B conformation. You see what I mean? So, and then you say, see, we can measure that very nicely with this. Okay. I'm almost certain that people are going to ask you, what about the thing on the left, and why is there something suddenly appearing there? Good. Sorry, what?
So I should not show.
No, I think it's fine. I think the first thing that you can do is when you talk about the first 4, okay, when you look at the first 4, clearly you have sort of a mirror going on there. You see, these 2 disappear, and in exchange, these 2 appear. So one could even imagine that, W171? Sorry, W171, no, W460 is the equivalent of W171. You know what I mean? That they sort of, that basically the rotation of Q390 brings with it the movement of water 460 into position 171. You see what I'm saying? So I think you can highlight that here. You see that basically these 2 disappear, therefore these 2 appear. You see? And then what I would do here is sort of hide the lower part if you don't need it. I think you can go just with the upper part. Okay, like that. Because also the densities are going to be easy to see. And then the other part you can talk later about it. So the lower part, when the, E384 appears, that you can talk about it later. So, but I would just use the first 4, and then of course, because you have more density, you can show the densities on the right. You see what I mean? So yeah, that's what I would do. Okay. Then under this condition, go back. Okay. So yeah, you have this kind of rotation there, isn't it? So. Okay, then let's continue. Okay, this one, to be honest, I would have earlier. So that people can see a bit the orientation, because for example, Yuhei was mentioning the driving force. Well, I mean, 8HDF is there. And it has received a photon. Something has happened with it. So with this one, we can say, oh, so what could be the driving force of all of this? Well, there is one particular element that we see very differently with and without 8HDF. This element is Q390. And we can see that Q390 lies precisely within the interface between 8HDF and FAD. And we see this movement that we cannot see in the absence of 8HDF. So we have reason to believe that the driving force is the interaction between 8HDF, Q390, and FAD. So our first goal was to carefully analyze how Q390 behaved in the dark, behaved in our kinetic. You see, so you start with this guy here, maybe the 1 microsecond one or something like that, before you have you see the E384 there. I don't know if you want to keep it or you want to remove it or something, but what I mean is make it a bit cleaner at this point. Do you see what I mean? That you have Q390, 8HDF, FAD, and the 2 waters. Or select one where you can only see that. You see what I mean? And then you say, see, we have this kind of behavior here. Yeah? And in this one, you can show the 2FO minus FC of the dark state for both with 8HDF, where you have the double conformation, and without 8HDF, when there is a single conformation. And we say, see, even in the dark, the presence of 8HDF appears to affect the dynamics of this residue. So what's the driving force? The driving force is still the same as before, but the presence of 8HDF modifies the dynamics and brings the most important, or changes the control of the reaction to a different residue, namely Q390. You see? You see what I mean? So the driving force is still photon absorption. The main difference is that the TPP has been modified. You see what I mean? And they have been modified by Q390 sort of jamming itself into it. Which brings us to the next point. Can you continue? So this stuff, if you need it, keep it, but I would tell you leave it in the supplementary. I know that it's a lot of work. I know that it hurts when you leave technical stuff in the supplementary. In general, I don't think you need it here, and it makes it more complicated to understand. Okay? So I would move this into the supplementary. And instead, I would go for a more careful analysis of other parts. So continue, please. So this supplementary, this you can keep. Yeah, and you say, see, by doing careful analysis, so of course we can see that there's a change in occupancy. So our first goal was to do a careful analysis of the occupancy. We used 3 different methods, and they all produce highly reproducible values. Instead of having it like this, I would say 3 different methods and show standard deviations. Do you know what I mean? And you just say, see, we use 3 different methods to determine the occupancies. One based directly on emit maps, one based on estimating the occupancy based on deconvolution of the activated fraction, and a third one based on refinement. That's it. If people ask you, you have the supplementary data in the background, but you just say we use these 3 methods, and all of them produce very comparable occupancies. Here we can plot them over the entire reaction, and these are the values with this standard deviation depending based on the methodology that we use. You see what I mean? And that's it. And so you don't spend a lot of time sort of going through that. Okay, continue. Again, so now, at this point, okay, I would go, so at this point, I would show the densities from the nature chemistry data. And I would remind people what you're doing, so how you expect things to behave. Okay? So namely, no, more general. So the key point here, I mean, maybe we need to sit down and discuss it a bit more. Like this, it may not be the best option. But clearly to me, if you go further, continue. So I am not convinced by what you said that first E384 moves and then N395 moves. I don't think that is the case. Or I don't think that you have enough resolution for it, time resolution. I think that what happens is that it's concerted. Now, how do I believe that the concerting effect works? Well, because the position where you should have the rotation is occupied by Q390. And And now Q390 over time moves away.
The position is occupied by water.
No. Remember that this is much bigger. What about this distance?
Uh-huh.
Do you see what I mean? This one to this one.
Mm-hmm.
Okay? So my guess is that this one to this one, okay, is too, what's it called? It's too close. The rotation cannot happen because Q390 is blocking it at that point. Okay? So when Q390 moves away, yeah, you may get a dynamic water there, but that water can be easily moved at a later point by the glutamate, isn't it? And so what's happening is that initially you have the Q390 sort of intruding there and preventing the rotation, isn't it? Okay? Then at some point, at its own dynamics, Q390 moves away from this position and towards the 8-HDF. It collapses its occupancy in the 8-HDF direction, isn't it? Okay, and then it leaves a cavity here. Then in the first step, it's occupied by water, but because when you have something occupied by water, remember this can be easily displaced. So because it's now occupied by water, instead of basically being occupied by the big blob here, isn't it? Then now the water can be pushed around and moved around, allowing for rotation here and concurrent movement of E384. So now what we have is a different, so that the rate limiting step has changed. Previously, the rate limiting step was N395. Now the rate limiting step is Q390. And that is because you have the 8-HDF with which the interaction with Q390, which forces the interaction with Q390, even in the dark state, to change. So here we see how the kinetics are modified by a different starting point, induced by the change in the structure derived from 8-HDF. You see it now, you have a story. You see what I'm saying? So that's why my suggestion is that you get this kind of orientation. This is the important orientation, because it's the one where you can clearly see this guy sort of pushing here and getting red density there. So what you should do is take the structures from nature chemistry to produce these guys. And what should happen that here you have nothing, because Q390 will already be rather here. There are some signals on Q390, if I remember correctly, but they're much weaker, and they're in, it's already in this direction. Here you can show the big signal and say, see, it's moving away. So now that's why we can have the pathway. So we have an additional gating mechanism in the pathway, isn't it? What could be the use of this? Well, for example, one use could be to make N395 even less accessible by oxygen. You see, in the dark state, we have this guy blocking much more of it, isn't it? So okay, the entire reaction may become slower, but in exchange, once the whole thing relaxes, and this goes back to the dark state with the changed redox state, now instead of having only 395 and then essentially solve it, isn't it? Now we have N395 and Q390, which means that any oxygen molecule that may want to enter to oxidize the FAD is going to have a much more difficult path. And so this would explain why reoxidation in the presence of 8-HDF is so much more difficult. You see, and now you have a structural explanation for the observed data. You see what I mean? Okay, so the story is there. You just need to, again, de-technify it, isn't it? And think about what the evidence was before and what your evidence is saying. Okay? So it's all there. You just need to massage it a bit. Okay? So my suggestion, therefore, is that you show also the timescales. So you can do kinetics of the different states, isn't it? So what you should show is timescales. What are the timescales of all of this? You showed already that this guy happens in, what is it, 0.7 microseconds, isn't it? Q390. Yeah, 0.7, okay? How about the others? You have the time constant from the Nature Chemistry paper. So you don't need to show many figures. What you can show is your figures. Because again, what you don't want to do is don't want to give the impression that your work was simply filling in the gaps of previous work. That's not good. And your work is not that. It's explaining something new, isn't it? So therefore, you don't want almost every slide to have pictures from a different paper. You want your slides, your work slides, to have your pictures. So one way of avoiding that is, well, basically, you have already explained how everything works. Now you just give the time constants. And you say, see, the time constants in the absence of 8-HDF tells us that E384 moves within, I can't remember, it's in 300 nanoseconds or so, isn't it? Okay, in our case, however, is with a time constant of 10 microseconds. Clearly, we have here a tenfold difference, indicating a delay in the reaction. Further, in our initial data, we had a time constant for the rotation of N395 of, I don't know, 30 nanoseconds or something like that. No, it was already done, isn't it? So within faster than 10 nanoseconds, isn't it? Okay. Meanwhile, here we see that the time constant is comparable to E384. What is this telling us? What this is telling us is that now the starting point of the reaction is not the rotation around N395, but the movement of Q390. Isn't it? Easy? Okay? So that's the direction I would go. Okay? And so I would show more such graphs, okay? Make it a proper kinetic analysis, okay? Show more graphs like that. I would show the general structure that you showed, so this kind of overall overview. You don't need to compare, for example, the FAD. You just say, see, here we see the FAD existing in our signals around the FAD existing for a long period of time, up to milliseconds. Okay? If you want to, in your conclusion, you can do a comparison table, where you say, lifetime of signals around the FAD, possibly FAD dot minus, unstabilized FAD dot minus. In our case, I don't know, millisecond time scale, isn't it? In the previous case, microsecond, isn't it? Time scale of movement of assembly of the TPP. In this case, microseconds, isn't it? In the previous case, tens of nanoseconds. You see what I mean? And so you provide that and you say, see, clearly, in the presence of 8-HDF, we see a general slowdown of the reaction, which is, in general, an indication of a higher stability of the intermediates, isn't it? If these intermediates live longer, it means that they're more stable, isn't it? And we believe that the reason is that Q390 is acting as an additional filter, preventing interactions with outside, oxidating agents in the outside world. Something like that. And so careful control of the oxidation filter Q390 allows for the transient protonation pathway to be built or not at precisely the right time. Okay? Okay? And again, if you want to sit down, we look at it a bit more carefully and so on, I'm sure we can build a nice story from all of this. Okay? And both for your defense, and also I think that we should be able to produce a super nice story for also writing a paper about this one. Like, clearly, we have a couple of very nice sets of data, which leads me to my next question. How is the Q390 photoreduction study going? Anyone? talked to Polly about that. Q390, we already have the mutant, but we've never, and without 8-HDF, it has no effect. Right? I would be interested in finding out what happens with 8-HDF, because hopefully, with 8-HDF, but if we mutate Q390 to alanine or something, the effect should be that it looks like there is no 8-HDF, so that your results can be negated, isn't it? As it is, as if 8-HDF would not be there. If that's the case, we can clearly show that the stabilization towards reoxidation derived from 8-HDF comes from the presence of Q390, isn't it? And that would wrap up the story and position Q390 as a kind of reoxidation filter. You see what I mean? Okay? Good. Wonderful. As I mentioned, you just need a bit of tweaking. Okay? Great. Okay, good. So I think if there are no more questions after this much of a discussion, I think we can leave it for later, isn't it? Let me know when you want to organize, because I think that we really need to sit down and look at the data a bit carefully, isn't it? I think also in advance of the beam time. Will you be at the beam time next February, or will you be gone already?
I'm not sure.
Yeah. Well, I'm just saying, either way, we need to plan for it, and we need to plan for what's missing here. Because I think that the only issue that's missing here, or I think that there are certain points that are missing, and we need to make them. Isn't it? And so with 36 hours, we should have plenty of time to fill in the gaps here and really produce a super nice kinetic where we can really see something. For example, clearly there you need a, 10, 20 millisecond data point. I mean, if you look at the kinetic, the last point is going up in both.
Yeah.
Okay? Is that an outlier, or is it really going up? So you need a 30 millisecond time point. So we see if the 30 millisecond time point is further up, or if it goes back down to the original state. My guess is it goes back up. Basically, protonation happens at about the same rate. You see, at about 37 milliseconds or so. I mean, in the tens of millisecond time scale, protonation is happening, and so what happens is that the antioxidation filter is going back to its original position to close up the entire thing, isn't it? And then therefore you end up with the breaking of the TPP at about the same time scale, isn't it? And the movement of Q390 to block the passage. You see? That would be my suggestion. Good. So yeah, that's why definitely we need a couple of extra points there. Yeah. Okay.
Okay.
So I don't know. I have class today until 2 p.m. isn't it, or something like that. I need to prepare a midterm. After that, today could be good. Tomorrow, actually, because of the midterms, I don't have a literature seminar, so bachelor literature seminar in the afternoon, which means that I could also. So I could also have it tomorrow. Wednesday, it's also fine, I think, at this point. So Wednesday, I don't think I have.
Wednesday, beam time is starting.
Sorry, what?
The beam time is starting.
Yeah.
Yes, sorry.
Yes, I know. But I mean, the idea is not to be all the time sort of there. I mean, they're going to have to do some stuff at the beginning where I will be busy, but not necessarily all the time, isn't it? I'll have to have my phone nearby. So Thursday, I have class early in the morning, but after that, I'm kind of free until I would say about 3 or 4 p.m. when Junpei will arrive, isn't it? Then my guess is that I'll have to spend a bit of time with Junpei. But maybe he's also happy to look at this, isn't it? So yeah, okay. Just what I'm saying is, let me know over this week so that we can sort of design a plan to finish up or to finish up analyzing this. Okay. what's the situation with your freeze? So what's the situation with the refinement?
So the situation now is because I did a lot of extrapolate based on different residue,
Yeah.
but I really cannot find the better better M value to do the refinement based on extrapolated structural factor.
Of Q390 or what?
No, I mean because for to refine the whole protein,
Right.
I still need to choose a M value to refine it. Yeah.
Yeah. And so which one have you chosen?
I've tried 4 point something is corresponding to the water, then for n equals around 15 is corresponding to N395. I forgot how about the D321.
Okay, well, and how about Q390? Also about 5 or something?
Yeah, around 5.
Yeah, then choose this, and the other ones you go by occupancy based on that. Do you know what I mean? The other ones you model them at whatever their extrapolated value is, you know? But then you lower the occupancy corresponding. Do you know what I mean?
Okay.
Okay.
Mhm.
And so, well, we can talk about how to do it.
Okay.
My suggestion is that you only need to model one structure once, or one movement once. I don't get the feeling that you have a lot of gradual movement.
I think only tyrosine 49.
Yeah.
Where is it? Where are you? Tyrosine disappeared. Okay, so for tyrosine 49 is close to HDF, and there's some, I think, a bit
there's a
movement
bit of
with main chain.
Yeah. Yeah, that could be the case. We can take a look.
Yeah.
Okay. But I think that so let me say it like this. I think, for example, on the nature chemistry data, we could have saved us a lot of time in refinement just by having done the cluster analysis and having realized that there are two conformations. Do you know what I mean? And then say, this conformation looks like this conformation looks like that. Okay, maybe the occupancies changed over time, but these are the two conformations, full stop. And I think you have a situation that is similar, where with Q390 it's very clear. You have Q390, you have these two states, isn't it, like this? And so it's either here or there, isn't it? And so the occupancy changes, but that's kind of it. And I think that for a lot of the other ones, you have the same thing. So the idea is, find the one that has the highest occupancy, refine it there, and then for all the other ones, you just you just refine the occupancy. Is it? By either beta or by M estimation or whatever you want. Okay?
Okay.
Okay? So that's how I would do it. And so, again, that's why my idea in the end is that you have a movie where we color by occupancy, and you can see sort of waves of occupancy radiating from specific areas of the protein. Is it what I mean? That's how I would think it should be. Okay, I think that we're done, isn't it? Then yeah, let me know when you can meet.
Okay, thank you.
Thank you very much. Yeah, as you can see, lots of work, but analysis.